In the following, we introduce our model of cognition, referred to as MOM or model of models, to be used for constructing an AGI. Then we elaborate about three aspects of cognition in our model, which are will, planning, and understanding. Next, we dive into how knowledge can be represented to implement these three aspects. Finally, we'll see some examples. To account for a better prior than the current one in deep learning, or especially in large language models, we propose a neurosymbolic hybrid cognitive model, where the ideal and mature state of the AI is mainly symbolic, while the evolution process required to reach this stage is accomplished via deep learning. Here we present only the ideal final state of cognition. Our basic assumption is that cognition is about operating on accumulated knowledge with the guidance of an appropriate will. First, we'll start from will and ask ourselves why will is needed in cognition at all, because cognition is mainly about logic, isn't it? No, it's not only about logic. We attach will to most of the interactions we have in the world. It means that a full model of any entities consists both of knowledge about it and some will associated to it. Planning starts from will in the form of vector field, in which we have two types of will: to get away from something or to get to something, or both. We assume that the knowledge models are aligned with the will field after some extensive learning period. Then a planning can be initiated, involving the available models. It could yield, for example, an intuitive solution, though usually it is incorrect. Hence, for a better solution, some amount of effort is required. While planning works in top-down fashion, understanding works in the opposite way. So far, we have seen the macro view of cognition. The next step is to dive into how knowledge models are represented. We represent each object or class along with its features and actions, or in the equivalent graph view on the right. Remember that all these elements are also classes themselves. We propose also to include a measure of relevance to prioritize differently the elements that belong to the class. Given knowledge basic elements, we can represent a state as a group of objects, and action as those that operate on one or more objects in a state. Also, the actions are derived from will. Also, since we use forms, we can aggregate several objects or actions by abstraction or grouping. Here we utilize the knowledge representation for inference mainly to fill missing information. Given a knowledge map, suppose we perceive an input, which triggers some object in this map. Then an inference process starts to characterize this object by propagating and activating relevant features either via one step or more. Similarly is with the following triggered objects. But the inference scanning is not blind. It is usually also guided by will, a basic form of it. Simple questions type of will. This inference occurs not only in understanding but also in planning, specifically to comprehend the problem and the goal. Now we'll see some examples. Here we simultaneously perceive incoming data and try to comprehend the gathered info received so far. First, it triggers the fish object. Then, guided by what question, it extracts the relevant features. Here the dog class is triggered, and then an instance of it is accessed assuming it to be the last discussed dog. Again, we use will to extract the relevant feature. Given some math problem example with group objects in the problem state, we can induce the appropriate will field for it and see an example of abstraction. And see an example of proposed solution. In this example, we derive the states from a story string. We can see inference, we can see past state creation, this is a mixed example to show that the first step is understanding and the next step is planning. In this case, it is kind of a story completion task. Hence, the next task is to solve the problem or to figure out the how. We do it by decomposing will or actions to reach as most detailed solution as possible. As mentioned previously, planning is a top-down process. Alternatively, we can view the solution as a story to be understood by some other listener. This evolves as usually as a stream, only this time we try to reconstruct the original will from the detailed actions. Hence, it is a bottom-up process. Also note that at each state generation there is also local inference processes, which can be regarded as internal will, as opposed to the external will, which we try to reconstruct from the story.